Okay, second problem from class today, an equilibrium problem. We went through this in class, but just in short, NFL goalposts. And based on my experience in graduate school, I had people that after game would want to climb up here on the goalposts and hang on to celebrate the victory. And the question is, what additional force is the ground going to have to supply to keep this goalpost from falling over when a person is standing there? I gave the person a mass of 95.0 kilograms, and all of the specifications here are actually NFL specifications. They're not college specifications. The single standard, that's this vertical portion, needs to be buried at least 53.0 inches, so I put it at 53 inches. Notice I said treat the ground as if it supplies one horizontal force at ground level, which I called F1 in my figure below, and a second horizontal force at the bottom of the hole, which I called F2. So I've drawn two pictures to get us started. First, a top view. So this top view, we have the goalposts. Here's one goalpost going straight up. Here's the other goalpost going straight up, and I have the person sitting over here on this goalpost. The gooseneck is coming back here, and then it goes down into the ground there. So R is the horizontal distance from where the pole goes into the ground to where the person is standing. Here's a side view, so you can see here is that R distance. So I'm looking, this side view is looking at an angle like this. So this R is that R distance. This H is the height of the crossbar. And then I have this D is the depth that it's buried. And you see here I have the F1 and F2 indicated as in the words above. So, how do I solve this? Well, as indicated with the words at the top, this is clearly an equilibrium problem. So it's an equilibrium problem. I have two equilibrium conditions. Sum of the force vectors equals 0, and sum of the torques equals 0. Now, if I look at my picture, I have three forces. I've already drawn my diagram with the forces that are acting on this that I care about. Notice I don't have the weight of the crossbar because I'm only asking about the addition needed for the person. The person has a force gravity mg that's acting down, and then I have two horizontal forces. If I were to try to use Newton's second law, the sum of the forces is 0. In the vertical direction, I actually don't even show the support force down here. There has to be a support force here, but that's not going to help me find that F2, the horizontal force. If I do the horizontal forces, some of the forces that are horizontal, I'll just get F1 equals F2. Well, that doesn't help me find what either one is as well. So I'm going to have to use the torque equation. I knew beforehand, really, that I wanted to use the torque equation. How did I know that? Because I have two unknown forces, and the only one I care about is F2. So using torques, if I sum the torques about where F1 acts, F1 will make no torque. And also notice that the force support will make no torque about that location. So I am going to sum the torques about point A, and using this equation that the sum of the torques come to 0, I will be able to solve. So note now that about A, I'm going to have a clockwise torque due to the force of gravity. That's going to be a negative torque. I'll have a counterclockwise torque due to F2. That's a positive torque. So if I do the sum of the torques, and of course this is about an axis coming out of the screen, the sum of the torques is equal to, and I'll put here specifically 0 for the distance perpendicular for the force support, plus 0 times force 1, plus D times force 2, minus R times force of gravity. So this is getting done real quick. I only have two terms here. I have R times force of gravity is equal to D times force 2. Divide both sides by D. And I have force 2 is equal to R over D times force of gravity. Now what is R? If we look at my diagram here, we can see that I have a right triangle. One side is 18 feet 6 inches, all divided by 2, in other words, 9¼ feet. The other side is 2 yards according to the word, so 6 feet. So using the Pythagorean theorem, R is equal to the square root of 9.25 feet squared plus 6 feet squared, which comes out to be, according to my calculation that I carefully did before doing this, 11.02554 feet. Now clearly I don't have that many significant digits, but I write them all out for now. What is D? D is that 53 inches, or 4 feet 5 inches, 4 and 5/12 feet. And so I can just put my numbers in now. 11.02554 feet divided by 4 and 5/12 feet. If you're interested, that 4 and 5/12 is 4.41667 feet. Multiply it by the force. Well, the force is the mass times gravity, so his mass is 95.0 kilograms. Acceleration of gravity is 9.80 meters per second squared. You put that in the calculator, crunch it through, and I find that force 2 is 2,324.1 newtons. Now, of course, I only have 3 significant digits, so the real answer is force 2 is equal to 2,320 newtons to the best of my significant digits. So that's how much force the ground would have to supply additionally to keep the goalpost from tipping over when a 95 kilogram, now you might wonder, how much does a 95 kilogram person weigh? Well, they weigh 9.8 meters per second squared times that 95 kilograms, so 931 newtons. To counter that 931 newtons, you need a force of 2,320 newtons down there at the bottom. Big forces going on there. Now, does the question make sense? Certainly the answer, so I think we're done there. Short problem.